Hi everyone. So let's get started with the concept of a limit by talking about the two basic problems which will lead us to the idea of the limit. Those two problems are the tangent problem and the velocity problem. So let's take a look at my slideshow. And you should be aware of these problems back from the high school geometry. So if we remember the tangent to a circle, right? The general tangent problem that we are trying to tackle today is as follows. How can we define a tangent to a curve? So how to find, and ideally we want to define it rigorously, a tangent line to a curve. And let's say that a curve is given by a function, y equals f of x. A simple variation on this question is how to define a tangent to a circle. And that you definitely know the answer to from high school geometry. Pause the video for a second and try to remember. What is it? How do you define a tangent line to a circle? Okay, now that we're back, and of course you hopefully remembered that we defined the tangent to a circle as the line which touches it or has exactly one point in common with the circle. It intersects the circle exactly once and only once. But we will see in a second that this definition does not work well for more complicated curves. Why? Imagine something which is like a cubic curve. How does that look like? Something like this. Here it is. And these are the two lines through the point P. So pay attention to this point P. We have the blue line L, which does intersect the curve exactly once, but clearly it's not tangent to it. And on the other hand, we have what appears to be a good candidate for a tangent line, this T. But it does intersect it in two places, at P and also at this other point. So clearly this definition of intersecting the curve exactly once no longer works for more complicated curves than a circle. Good. So nonetheless, let's try and find a practical problem. Let's try and find the tangent line to a given simple curve, to a parabola, to a curve like this, y equals x squared. Familiar precalculus curve parabola. And let's be specific about it. We want to find it at the point P with coordinates 1, 1. In other words, it's pretty easy to draw it, but we want to find an exact equation. If I were to draw it, then of course it would draw like this. But what's an equation of this tangent line? That's what we will attempt to find. Do you have any ideas on how to go about finding the equation? The exact equation. Pause your video for a second and think. What are the key missing ingredients? Okay, hopefully you're back now. You realize that one key ingredient we have is the point through which the line passes. But what else is needed to write an equation of a line? Another data point could be either a point on the line, a different point on the line, or just a slope, right? So that's what we'll say. We're missing the slope. Let's try to find the slope of the tangent line. At least the idea of tangents is that the tangent line should point in the same direction. To be tangent means to touch, and that means that the slope should be given by the trend in the original curve, isn't it? So that would be our clue to finding this missing piece. So yet we are stuck without the second point, which would allow us to find the slope. So what are we supposed to do? Well, let's take a look at a good drawing. And the suggestion here is, if we cannot find another point on the tangent line, that's what we would like to have, but we don't. But it's not available. Then we'll take the next best thing, and that is the point on the curve, Q. So Q is the point on the parabola. It is not a point on the tangent line. So it won't give us exact slope, but it will give us an approximate slope. And the closer we get the Q, we can take the Q even closer and closer and closer. The closer we get to the original point P, the closer will be the approximation, the better approximation we will get. Okay, so let's see how it will work. So here's our parabola. Here's our point P, and we're taking the Q on the parabola. And we're trying to find the slope approximately using the line through these 2 points, P and Q. The secant. S is the secant line. Versus what we really want is the tangent line. But unfortunately, T only has 1 point, P, that we know, and that's why we'll have to deal with Q instead. So then the slope M of the tangent line is not the same, but we'll say approximately the same as slope of the secant line, MPQ, or we can write M sub S. And that is the change in Y over change in X between P and Q, right? So what is that? Change in Y over change in X. That is, we have to take Y coordinate Q, subtract Y coordinate of P, divide by X, Q minus X, P. But coordinates of P are known to us. So P has coordinates 1 and 1. What are the coordinates of Q? Well, let's say that the X coordinate is just X. Then what would be the Y coordinate? Pause the video and tell me. Do you know what it is? Clearly that will be X squared. Why is that? Because it's on the parabola Y equals X squared. So then we can continue by writing in all the coordinates. YQ is X squared, YP is just 1, XQ is X, and X coordinate of P is just 1. So we can approximate it by taking anything for X. So for instance, if point P situated at 1, of course, we cannot take 1, because then we'll have to deal with division by 0. So anything, take any x not equal to 1. Let's take x to be equal 1.5. What do we get? So then our m, which is approximately mpq, will be equal to 1.5 squared minus 1 over 1.5 minus 1. So use your calculator, you will figure out that it's 225 minus 1 divided by 1.5 minus 1 is 0.5. On the top we have 125. If you divide 1.25 by a half, how many times does it fit into 1.25? Twice, a little bit more than that, 2.5 times. So we can say that taking x to be equal to 1.5, then our m will be approximately equal to 2.5. Okay, is that the ultimate calculation? Can we do better? What do you think? Pause the video and think what would be, how do you answer this question? What can be better than taking x to be 1.5? Okay, come back and hopefully you realize that 1.2 or 1.1 would be better than 1.5 because we're getting closer to the point P. So our approximation becomes more precise. Okay, so let's take a look at a few such calculations when we take x closer and closer and closer to 1. This is a bunch of such calculations collected together in a table. So what is the trend that we're seeing here? The trend is that we're trying to get closer and closer to 1. So here we're doing it from above. X approaches 1 from the right. We'll indicate it like that. And in this right table, we're approaching 1 from below through values which are smaller than 1. So we can say that x approaches 1 from the left. What are we seeing here? What is the conclusion? The closer x approaches 1, the closer the values seem to approach 2. So we can write that m, which should be the value approximately equal to mpq, as q tends to p. So this m should be, or at least seems to be, getting closer and closer to 2. So we will write it symbolically like this. Limit of the secant slopes is the slope of the tangent line, or we can write it numerically with formulas. As x approaches 1, we will say that limit of this rate of change, limit of this secant slope is equal to 2. Now we're still kind of not sure. So far, all we have is the so-called calculator evidence from the table that we've seen before. Okay, so, but nonetheless, assuming that that is correct, let's use the point slope of a line, this form of the line, to write the equation of the tangent line. Pause your video for a second and try to complete the answer to this question. Let's get the equation of the tangent line exactly. Hopefully now you're back, and all it takes is filling in all the unknowns here, all the stationary points. Y and x, of course, are the running variables. So what do we fill for all the missing data. Slope is, we assume, is equal to 2, then y1 and x1 are coordinates of which point? Of the stationary point, of the point P, and which are 1 and 1. So if we simplify, that's equivalent to y minus 1 equal to 2x minus 2, or y is equal to 2x, add 1 to both sides, you'll get this equation. Okay, let us now understand graphically what happens. Visually, as q approaches P from the right, we see that this slopes, you see that the secant lines rotate. How do they rotate? They rotate clockwise to approach the pink tangent line. And as you approach Q to the P from the left, then you see similar rotation like this, right? But now it's counterclockwise. Let's discuss now a very similar velocity problem. So the velocity problem is this question. Let's say that you're driving your car and you're looking at your speedo, and the speedo, your speedometer seems to be showing a new speed at each moment in time. So the question here is, how do you find and even rigorously define a velocity at a given moment in time, at a given time? Let's say that your given position as a function of time. How should you define the velocity? Okay, and to be concrete, let's look at a specific problem again. Imagine that you climbed some high tower like the one in Toronto, which has an observation deck 450 meters above the ground, and you drop the ball from this tower. Can you find the velocity of the ball after 5 seconds? The ball speeds up as it approaches the surface of the Earth, but what is the speed exactly 5 seconds after it is released? If you think about it, if you studied physics, you actually know how the position changes with time. The position, according to Galileo Galilei, is proportional to the square of the time that it has been falling, if you released it without giving it any velocity initially. That is, S of t should be proportional to t squared, which is the same as saying that S of t is equal to some constant times t squared. So if you studied physics, you probably know what this constant is. In the standard system, meters and seconds and kilograms, that will be, of course, 4.9, or acceleration. Acceleration due to gravity divided by 2 times t squared. So given that, let's try and figure out this question. Given that we know that the position is changing like this, can we find the velocity after 5 seconds exactly? Well, we know that just before 5 seconds, it was a little slower than at 5 seconds, then after 5 seconds. So maybe, even though we cannot find, we have no idea how to find it precisely, then we still understand that the velocity at exactly 5 seconds can be understood as the average, right? The average rate of change over, so average rate of change of what? of position, and that is del S over del T. And we want to catch this rate at around 5 seconds time. So maybe then we should compare S of T plus some delta T plus some increment minus S of T, where T is 5. T is 5. Oops, I lost it. Let's go back and start again. So we are saying that V of 5 should be approximately S of 5 plus delta T minus S of 5 over, of course, over the increment in time, which is delta T. Or we can say, okay, final time minus initial time. And we'll get delta T on the bottom. So on the top, then let's plug in the formula for S of T, which we said is 4.9 T squared. So we'll have 4.9 times 5 plus delta T squared minus 4.9 times 5 squared. Then we can simplify. 4.9 goes out. What do we have inside? 5 plus delta T squared. We'll get 5 squared plus twice times 5 times delta T plus delta T squared minus 5 squared. This will cancel. So we will get 4.9. We'll get 10. 2 times 5 is 10. Delta T plus delta T squared divided by delta T. We can even take the delta T out from the top. We'll be left with 10 plus delta T divided by delta T. It will cancel. So we'll get 4.9 times 10 plus delta T. So if we take delta T equal to 0.1 second, that is, we would be approximating V of 5, velocity after 5 seconds, with the average rate of change, with the average velocity, the average from T equals 5 to T equals 5.1. Then we will get that V of 5 is approximately equal to 4.9 times 10 plus 0.1. In other words, 4.9 times 10.1. How much is that? So it's 49 plus 1/10 plus, so that is 49 plus 1/10 for 4.9, which is 0.49 meters per second. But that is just one calculation where we've taken the increment to be 1/10 of a second. Okay, good. Here are some other calculations. So here's where we've taken this increment delta T to be 1/10 of a second, and that's, oh sorry, oh that is 100th of a second, my bad. Yes, that is the interval corresponding to time increment of 1/10 of a second, and that's the average velocity that we get. But of course we can do better, and we are looking at smaller and smaller increments, and what happens as the time increment approaches 0. So we can say that we want to tend delta T to 0. And it seems like the average velocity is approaching certain number. What do you think this number is? We can guess that it is 49. Again, this is just calculator evidence. We want to do better than that, but for now, that's all we have to go on. And we will say that the average velocity in the limit is becoming closer to 49 meters per second. So we'll declare that the instantaneous velocity that we are trying to define, that we are trying to understand velocity at exactly 5 seconds, is the limit of these average velocities, and we'll set it to be 49 meters per second. But of course, this is just calculator evidence, and the question for next time is, can we define and find it? Can we find it exactly? Means without relying on calculator and so on. Think about it, maybe read ahead, and we'll discuss this and more in class. Take care, guys. I'll see you in class.